Welcome to the lecture on the normal and standard normal probability distributions. In this lecture, we're going to be going over quite a bit, and we're specifically really looking at z-values, we're looking at proportions and probabilities, and looking at a standard normal probability distribution overall. So we've already looked at what a normal probability distribution is. A normal probability distribution is essentially a distribution of data or the probability of occurrence where the distribution is normally distributed. It's a continuous distribution that's bell-shaped. It has a single peak at the center of the distribution. The distribution is symmetrical, and it's also asymptotic. Which means that it never approaches, or it approaches but never touches the x-axis. And you can also completely describe it by the mean and the standard deviation. So if you have the mean and you also have the standard deviation, you can basically talk about the location, and you can also talk about how spread out the distribution is. And also, there's a family of normal probability distributions. It's not that there's one standard probability distribution, although that's what we're about to talk about. So when you have lots of different probability distributions, it's difficult to talk about them in the same breath when they're all looking at different units of measurement. So, yeah. This is what we've looked at prior with the empirical rule. This is also a normal probability distribution, and when you have data that's normally distributed, you have the ability to use the normal probability distribution and the empirical rule and the rules associated with that to be able to basically take care of or interpret all the probabilities in that distribution. So with a normal curve, with a normal probability distribution, you have a tail and you have two halves, and you could literally just fold this in half. The tail and the left hand side is the exact same as the right hand side. The mean, median, and mode are all straight in the middle. And the tails theoretically extend on forever. An example of this would be like Brett Favre. If you look at how many football games he played in a row, he played something like 330 games in a row, where you have the average probably number of games in a row is like 15. The max game, I would probably even say it's less than that, maybe like 5 starting games in a row. And looking at that, he's got a z value that goes on forever and ever and ever and ever and ever, and he's like really far outside the normal bounds, and everyone else is really tightly compacted, but he's really far out there. So there's lots of instances where you do have normal, or you do have data that's really far out there, and so that's why it does theoretically go on forever. So with the family of normal distribution, like I said earlier, you can define a distribution, a normal distribution, completely by its mean and by its standard deviation. And why that's important is when you have a particular mean, it tells you where the location is. Where is it on this number line? Where is it actually located? And then the standard deviation tells you how spread out it is. And so we've got measures of location, measures of spread outness. And so if you look up here in the top left hand corner, you've got 3 different normal distributions that all have the exact same mean, but they have different measures of spread outness, or different standard deviations. And so the blue one is more spread out, where the red one is less spread out. And so you can see that the data is more tightly compacted, or has a standard deviation of 3.1 as compared to a standard deviation of 5 in the lower Elmira plant. Looking at the bottom, you have difference between different means, but you have equal standard deviations. And so you have 3 different distributions that look almost identical. They have that nice, perfect, normal curve, but they're very different. They're very different. They are all in very different locations. And so when you're looking at that, you've got to be aware of that. that you're looking at three very different distributions. And then on the top right hand side, you're looking at three different distributions that are in different locations, and they have different measures of spread outness. And so when we look at the mean and the standard deviation, we can tell a lot of information from that. So we've got the standard normal probability distribution. One of the difficulties with the normal probability distribution is when you're comparing different normal probability distributions, it's like comparing apples to oranges. You have one measure of spread outness. Let me see here. I don't think I do. I was looking for a tape measure. But we have, in the United States, because we are who we are, we decide to use, the U.S. measuring system that nobody else uses in the entire world. And then we go and try to measure things and compare our measurements to pretty much every other country. And it's really frustrating because it's like, yeah, we're trying to be on the same page, but now we've got to change everything in order to be able to make sure that all of our measurements are the same. And so that's something that's kind of like what the standard normal probability distribution does. It looks at all of the different all the different normal probability distributions, and puts them in the exact same metric. So they have the same, mean, and they also have the same standard deviation. So the big difference is that when you make any normal distribution into a standard normal distribution, you are making it so that the mean is 0 and the standard deviation is 1. So it doesn't matter what the data was previously, the mean is 0 and the standard deviation is 1. So that's the big characteristic of the standard normal probability distribution that makes it different from everything else. Now, we are also using something, instead of using, different, saying, okay, this is how many units it is away from the mean, hey, we are 10 units above the mean, or we are 8 minutes below the mean. We are now using z-values. Z-values are literally the signed distance between a select value designated x and the mean, and it's essentially the number of standard deviations away that value x is from the mean. So any normal probability distribution can be converted, like I said, and now we have the ability to compare measurements, and we're going to compute z-scores in just a minute as well. So I want to show you, I'm going to pull up a document, and this is your homework, as long as, what's that called? You're in the same semester. I'm sure that I'm probably going to keep it pretty similar to this, but I put this wonderful, let's see here, this wonderful chart right here. And with this chart, we have the empirical rule, we have the normal distribution, and then you can see, okay, when we're dealing with the population, we've got this, what we did earlier. Then when we're dealing with the sample, it's right here. And then when we were dealing with the standard deviations right here, and right here we've got the z-scores. Now, you can still put your original data, like for instance, this information right here is reflective of of this right here. The actually, that's not what it's reflective of. It's reflective of something. But it's got a mean of 5 with a standard deviation, it looks of 1.75. I think I borrowed this from something else, from a different question. But so you've got the mean of 5 and the standard deviation of 1.75. And so you'll notice when you add 1.75 down here, when you're dealing with the original data, you wouldn't be able to compare it to something that maybe has a mean of 7 with a standard deviation of 10, or something to that effect, or a mean of 7 with a standard deviation of 2. But now when we have everything on the same metric, where every single distribution has a mean of 0 and a standard deviation of 1, we're able to compare distributions to distributions very easily and get information about them. So next, what we're looking at now is, so we're dealing with z-values, like I said, and every single observation has a z-value. Okay. So in a probability distribution, area in a distribution is the representation of probability. So what we're essentially attempting to do is find the area within a distribution. What is the area between two points in this distribution? And so you can do this with Excel. If you do this with Excel, this is the formula that you're going to use, where you have the norm.dist, and then you use the value of the observation that you're looking at, the mean, the standard deviation, and then true says this is the probability. Like for instance, right here, if I were to say I have a mean of 283 and I have an x value of 285.4, and I've got a standard deviation. Let's see here. Let me figure out what the standard deviation is really quick. Equals 285.4 minus 283, and then that's 2.4 equals 2.4 divided by 1.5. And so this has a standard deviation of 1.6. So we've got a standard deviation of 1.6. So if we were to be doing this one right there, I'm going to put it into the PowerPoint. Let's see here. This is what it would look like. It would look like norm. Oops. Norm dot dist, and then we are going to put 285.4, and then we're going to put 285.4. Then the next thing is the mean, so that's going to be 283. And then the next thing is the standard deviation, which is going to be 1.6. And then after that, we're going to put true. And then what that would give us is the z value of the 285.4. And so the z value is literally 1.5. And so, we already had it, but so the z value is 1.5, so if you put this in there, that's what it would give you. The other option that you have is to use something called a z-table. Now, I'm going to pull up a z-table, the full z-table really quick, and I made this available to you guys in Canvas. This right here is a z-table. There's lots of different types of z-tables, and what you need to always look at is in the top right-hand corner. This z-table tells you that these values in here tell you the probability of a value being at that z-value or at a negative z-value or below. So if you get a negative z-value or below, these values in the middle will tell you the probability of you randomly getting that z value or below. Okay, so very specifically here, we've got, like I said, 285.4, and we need to find the z value. And so the z value we can find by using the z formula. And so we're going to use the z formula, and the z formula is going to be... let's see here. I'll put it right here so that way you guys can see it. So we've got the mean minus, the observation minus the mean. So it's going to be 285.4 minus 283, which gives us 2.4. So we've got 2.4, and then divided by the standard deviation. And the standard deviation is, like I said before, 1.6. And when you have 2.4 divided by 1.6 equals 2.4 divided by 1.6, that's going to give you 1.5. Okay, so what I just did here, like I said, is we had the 2.4, which is the mean, we have x minus mean divided by SD equals z. Okay, And so the z value, then we come over here and we find 1.5. Like I said, these are only negative values, but you can still find negative 1.5, and you find the intersection of negative 1.5, and then you find, so you see right here at the end, 1.5. Is there anything after that? No. So it's 1.50. So what you do is 1.50, and you find the intersection of those two, and this right here is the probability of a value below a negative, or the probability of a value above a positive. The probability of a value below a negative z value, or the probability above positive z value. So this is a positive z value, and so the positive z value of 1.5. So the what we need to do is we need to say, okay, we've got 0.0668. And use the complement rule. So we're going to do 1 minus 0.0668, and that gives us that's going to give us 0.9332 equals 1 minus 0.0668. So what that tells us is that there is that the probability of an individual having a score lower than that is 0.9332. 0.9332. So the probability of it being at 1.5 standard deviations above the mean or below, 1.5 standard deviations above the mean or below is 1.5. But if you wanted to know, hey, what's the probability of being between the mean and that value right there? What's the probability of being between the mean and that value right there? What you would have to do is take the 0.9332 minus 0.5, and that gives you 0.4332 probability of between mean and x. Then this right here is probability of being below x. And then the let's do one more. Let's see here. 0.0668 is probability of observation being above x. Okay, and so you've got a lot of different probabilities floating around here, and what this really means is, okay, you've got this value, and you want to know, where does this value reside? Where, like, what does this value actually mean? How does it relate to everything else? And so when you have these probabilities, you have the ability to just make more inferences. Okay, so let's take a look at another example. In recent years, a new type of taxi service has evolved in more than 300 cities worldwide, where the customer is connected directly with the driver via smartphone, e.g. Uber. Okay, so let's keep skipping down. You guys know what this is. Uber drivers follow a normal probability distribution with a mean of 1,000 and a standard deviation of 100. Okay, so we want to determine the z-value. So like I said, in order to find the z-value, we want to find the z-value of a driver who earns $1,100. In other words, where does he relate to everyone else? So you take x minus mu, so x is the value of the amount that he earns, which is 1,100, minus 1,000 divided by 1,000, which gives you 1,100 minus 1,000. So that's 1,000, or sorry, 100 over 100, which gives you 1. Okay. Same thing over here. We've got, what is the z-value of an income for a driver who earns $900? You do 900 minus 1,000 over 100, which gives you -1. And so regardless of whether or not you've got +1 or -1, I can pull this back up really quick. I'm going to show you, we've got this z-value. You go z all the way down to -1. Okay. -1.000. So this right here is the probability of being below -0, or sorry, below -1. And so the probability of being above -1 is going to be 1 minus this. Or if you have +1, a z-value of +1, this is going to be the probability of being above +1, or if you want to know the probability of being below +1, it's going to be 1 minus this. Okay. Okay, next. We've got finding area under the normal curve. What is the z-value of income for a driver who owns 790? Okay, so we've got 790 minus 1,000 over 100, which is going to be negative 2.10. And so we come down here and we find negative 2.10. We're looking at the second digit here, negative 2.10. And then you find the intersection between the two, negative 2.10. And that'll tell you that the probability of being below that is 0.0179. The probability of being above that is 0.5 plus 0.4821, which is going to be 0.9821 is the probability of being above that. So 98.21% of Uber drivers make more than $790, the probability of an Uber driver making less than that the probability of an individual making more than 790 is 0.9821. The probability of an Uber driver making less than 790 is 0.0179. So now we've got what is the z-value of income for a driver, which we already did this one. But what is the probability of it being, let's do this, between the mean and the one standard deviation above. And so we've got, once again, we found the z-value, which is 1,100. And so using the weekly income, what we need to do okay, so we find the on the z-chart, we find the one standard deviation above the mean. So the probability of, since it's a positive z-value, this is the probability of it being above that z-value. And so you take 0.5 minus the 0.1587. So let's do this. Equals 0.5 minus 0.1587, which is going to give us, let's see here, 3.4 or 0.3413. And so we have the, that's the area from 0 to 1. It's 0.3143. And the reason why I was able to do 0.5 is because 0.5 is the probability of being anywhere from the mean and beyond. So the mean and below is 0.5, the mean and above is 0.5. And so there's all this stuff too, but we'll just but if you wanted to know what is the probability of an individual being below that, it's going to be 0.5. You add up 0.5 plus 0.3413, and that's going to be 0.8413 is the probability of it being below one standard deviation above the mean. And if you notice the 0.8413, you're like, oh, we used the empirical rule, and if you remember with the empirical rule, that it didn't line up perfectly like that, or it didn't line up quite like that. It lined up a little bit differently. We just said 84%, and the reason why is because it's a whole lot easier to remember 84% than it is to remember 0.8413. But the empirical rule is pretty close to accurate, but we do round a little bit. So yeah. So looking at this as well, let's see here, what proportion of drivers can earn between $840 and $1,200 per month. The way to do this is you find the probability of 1,200 and below, and you find the probability of 840 and below, and you subtract the probability from 800. You subtract the probability of 840 from 1,200. Okay. So we've got right here the probability of okay, the proportion between 1200, we can find the z value. So let's find the z value for 840. So 840 minus 1000 divided by 100 is going to be a z value of negative 1.6. So we find negative 1.6, and that right there is the z the probability of being below negative 1.6. So we have, let's see here, yeah, 0.0548. And then right over here, what is the for an individual who earns 1200? You do 1200 minus 1000 over 100, which is going to give you a p-value, a z-value of 2. And so if we find a z-value of 2, you come right here and you're like, oh, but that says 0.0228. Why does it say that? Well, once again, this is the probability of it being above a positive. So if you see the 0.0228, in order to find the probability of being below that z-value, you've got to do 1 minus 0.0228, which is 0.9772. And so you subtract the smaller probability from the larger probability, which gives you the probability of being between the two of them of 0.9224. And you can do the exact same thing in Excel. And what you would need to do is follow this formula, the norm.dist, and use the x, the observation that you're looking at, the mean, the standard deviation, and you put true, and true tells you this is the probability of being there or below, at that value or below. And it's much more accurate, and I'd highly suggest that you guys use that if possible. You'll notice that it's much more accurate. We'll look at that a little bit more as well. So here's another example. Here we're looking at finding a value for x using z. So Leighton Tires and Rubber Company wishes to set a minimum mileage guarantee on its new MX 100 tires. The test revealed the mean mileage is 67,900 with a standard deviation of 2,050 miles, and the distribution follows a normal distribution. We've got X is the minimum guaranteed mileage, and they use the formula for Z to solve that no more than 4% of the tires need to be replaced. So this is an instance where you're like, hey, I want no more than 4% of the tires to have to be replaced. So what is that value going to be? What is that value going to be? And so in order to be able to do this, we need to find first the 0.04 on the z-chart. Okay, so we're going to find, where does it say 0.04? And so we've got to look in the middle of here someplace. Where is the closest value to 0.04? And that's right here. Negative 1.7 and then negative 1.75 is what it is. Negative 1.75. And when we've got negative 1.75, we are going to use that as our z-value. And now, since we have the z-value of negative 1.75, so step 1, find the probability in the z-chart. Step 2, find the corresponding z-value. Step 3, multiply the corresponding z-value by the standard deviation. Why am I doing that? Well, the reason why is because I'm following the z-score formula, right? So the z-score formula is z equals the observation minus the mean over the standard deviation. So if you multiply the standard deviation to z, then it now makes it z multiplied by the standard deviation equals the observation minus the mean. Okay, so we're multiplying it by multiplying the z-value by the standard deviation, which gives us 67,900. Which gives us the value of, sorry, my camera's in the way, 3,587.5. Then once you get that 3,587.5, you add the mean, which gives you this final value of 64,312.5. And if you look right down here, I worked it all out in much more of a concise manner. So negative 1.75 multiplied by 2050 equals, this. And then you add on the other side. So this right here is the z-value multiplied by the standard deviation. So you've got the z-value, this negative z-value multiplied by the standard deviation. And then eventually you're going to add the mean to both sides to give you the 64,312.5. and you'll notice that it is what we're talking about is this value right in here. So what is it that this is actually giving us? This is saying the let's see here, the minimum guaranteed mileage. So we're guaranteeing that. So if you're like, hey, what is it that we're saying? We're guaranteeing that our tires are going to last a minimum of 64,312.5 miles. And if that means that only 4% of the tires are going to have to be replaced before then, and so that's a pretty good guarantee. Okay, if I use the Excel formula, this is what I was talking about with just how much more accurate it is. When you're dealing with rounding error, it can really mess a lot of things up. So this right here is the formula. It's to do the exact same thing, just with much more accuracy. So norm.s.inverse, this is going to, and then you've got the probability of x. So you do norm.s.inverse.0.04, and that gives you the probability of, or the z value that's associated with 4% being below that value. So like 4% being below whatever value you're looking at. So that is negative 1.7 dot 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 dot. And then from there you can do the same exact thing that we just did prior to this, but the big difference is, like I said, you are dealing with data that is just much more accurate, because we're not dealing with this truncated chart. We're dealing with the actual values that are supposed to be there. Although the Z chart is a really good tool, it does lop everything off at the end, and when you lop everything off at the end, you notice that the closest that we were able to get to right here is this 0.04, 0.0401. Well, that little tiny bit right there, that little bit of messing it up and other rounding errors, is the difference between the true value of x and the value of x that we calculated from the z table, which, like I said, it's not a huge difference, but it's a whole 1.41 miles, and so there's a difference of 1.41 miles just due to rounding error. And so that's how you'd use the Excel formula to be able to do the exact same thing. So in short, z-values are really great because they allow you to basically look at multiple different distributions at the same time. When you talk about z-values, you can talk about the probabilities much easier. You can talk about the probability of an observation. You can look at proportions. You can say, okay, this proportion of the values are below this z-value, and this proportion are above this z-value. But if I were to just tell you, hey, our the value that we're looking at is 8, I couldn't tell you based on the value of 8 the proportion above or the proportion below, or I couldn't tell you the probability of getting it. But when you tell me a z value, I can tell you, you can say, okay, this particular value has this z value of this. I can tell you the proportions, I can tell you the probabilities, I can just give you a lot more information about the value that you have. And so that's why z values are so good. We're going to keep on using them for the rest of the semester, so I'd highly encourage you to get really comfortable with that. And I'm going to make one more lecture on the homework. I just gotta, yeah.